is negative, it's some like a saddle point. It's a negative curvature one. So as you see here, everything is second order. Why? Because if you start from the metric by taking the derivative, there is a jargon is that is called connection. And one more derivative of this connection is what we mean by curvature. Curvature tensor, curvature scalars, curvature. So curvature, you take a two derivative. That means a two derivative in the action, that means the second order in equation of motion, right? So just from that part, it is guaranteed to be second order. Okay. Another thing is that so far we have not seen any strongly violating some Einstein general relativity. It seems to be working quite well. Now, as for the lambda, Einstein first, he was satisfied with this one, but he cannot get some static. So he thought just universe should be static and nothing changing, kind of some, I guess, religious belief or what or whatever. However, it was not possible, but by introducing this one, he could make it really eternally existing and unchanging universe. But later, in 1929, Hubble found that universe is expanding, so time dependent. So Einstein seems that he dropped out this one, introduced the lambda. It was he who introduced, and throw them out because he thought useless. He made a kind of two or some kind of blunders, but actually that's actually a right one. Actually, we'll need that. Okay. Now, then, do we need, if Einstein gravity works well, do we need any theory beyond Einstein? I'd like to start from the theoretical aspect and also observational aspects. From first, the theoretical aspect. In 20th century, later 20th century, like 1960s or something, so-called quantum field theory was well established, according to which everything should be understood as an effective theory. Everything is running, as a quantum effect is a running coupling and etc. Starting from the very high energy renormalizable theory, and we have to come down. That kind of argument. So if we do that, let's assume that maybe so string theory, so that will be up to the 10⁻⁹ GeV. So it's a well-defined in a very high energy. And we come down. Then what field theory teaches us is that it will have all the higher and higher powers. So linear and quadratic, cubic, etc. That's what quantum field theory tells us. However, Einstein gravity means only this linear term. So if you believe in string theory, and if you believe in the philosophy of effective field theory, Einstein theory cannot be complete from the theoretical point of view. There must be some higher order correction. Then why we do not see that? Because that higher order corrections are quite small, gravity is very weak. So we have not seen that yet. We don't have any such precise measurement, but eventually we should see that. If you believe in quantum field theory and etc. Right? That's what I want to emphasize. Another thing is a so-called holography. That's the outcome of the string theory, according to which you have a gravity theory. And so if you have some boundary, so we are interested in understanding quantum theory, let's say in 4 dimensions, that we just go 1 dimension up, so 5 dimensions, and then think about the corresponding classical gravity. That's the idea of the whole holography. But here, then how to convert, it is quite well described. However, anyway, so we do need some dual geometry to describe our quantum system. And it is, of course, not Einstein. So there are also, this is purely theoretical things. So here, this is gravity it may be some real thing. However, even without considering the real gravity world, we may just borrow gravity language to study quantum theory. It's a really new methodology of studying physics. Okay. Now, from the observational aspect, here let me just mention one thing, so-called Hubble tangent. So this Hubble parameter is essentially the expanding speed of the universe. So the data is like this. So if you just think up to only here, let me just plot, okay, up to 2013 or something, blue color measurement and the red color measurement, what will you say? Are they in agreement or disagree? They seem to be consistent because blue color is a huge red bar, huge error bar. Red color is also huge error bar. So with that large error bar, they seem to be consistent. However, so later, so the blue color is so-called based on the cosmic microwave background, which is really propagating freely in the neutral universe right after so-called hydrogen atom is formed. Then universe is essentially neutral. Before it was plasma, so light cannot freely move. And the red color is, we just measure very close object and see how fast they are moving. And that object is a supernova. So that supernova-based observation, red color and the blue color, both methods became very, very more precise. And so as you can see here, they seem to be different. So we say that in terms of sigma, it's close to 6 sigma. So if it is more than 6 sigma up to 7 sigma, it cannot be the result of any fluctuation. It should be real different thing. So we cannot say that the measurement is disagreeing because there is still chance that they may be due to some systemic error or some fluctuations, etc. However, it's a really bothering observation. So we have very standard picture of the universe, so-called the lambda CDM model. I will come to that part very briefly later. So that one is based on the Einstein gravity. So something may be wrong by observe this kind of phenomena based on this phenomena. So that suggests that we may need somewhat beyond Einstein gravity. Right? Okay, then for the beyond Einstein gravity, what should we do? That is the question. So when in the early 20th century, end of 19th century, when quantum phenomena just somehow appears, there's some contradictions and some new things are occurring. It's quantum physics we call. But we do need some any guide. Without guide, so China is very huge. Wherever I go, without any some map or the real personal guide, I may be lost, right? So we do need guide. So just like in the quantum era, it was hydrogen atom because that's the simplest one where we can see the quantum effect. If you choose very complicated one, you don't know which one is a quantum effect. You don't know what is the, so it's just a complexity and you are lost. So what is that kind of guide? Simplest one. So we are talking about the gravity. Let's not introduce anything else, only gravity. Then the only structure is gravity is attractive, then shrink everything. So crunch, that's what black hole is. So there cannot be any simpler object than black hole. That's why we are studying black hole. And believing that may give us some clue for the things that we are not knowing. In other words, higher curvature corrections and etc. Theoretically, we believe there should be. Another thing is our universe itself. Once we are given some any model, it will give us how the universe should evolve. So those are the two playgrounds with which we'd like to test the theory. Okay? So before beginning, let me just think Lovelock theorem, which says in 4 dimensions, if we are working on gravity, so in other words, metric, and interested in only second order, then the only action we can write is Einstein gravity plus so-called Gauss-Bonnet. However, so this quadratic term, Gauss-Bonnet, is topological, so it does not contribute to the dynamics. So in other words, we'd like to go beyond Einstein, but cannot go beyond because Einstein theory is the only one. So we are stuck. So we have to, it's a kind of no-go theorem. We have to go beyond. How? We do need something more, right? So we'd like to add some new degree freedom. Way is some higher curvatures, like rather than so-called Gauss-Bonnet combination, just these kind of things. But these will give us not the second order, but higher order. So it's highly non-trivial. So there are some very well-studied things. I will not go the things. Essentially, the essence is we have to introduce new degree of freedom. That's what it is. So as a result, so the first term was the Einstein gravity, but there can be some other pieces. So in the higher dimension, because a higher dimension is quite often from the holography, higher dimension helps. Starting from higher dimension, we may so-called compactify to come down to 4 dimensions. There are many reasons why we are interested in high dimension. There, natural lattice is the simplest extension in addition to the linear term and the constant term. However, in 4 dimensions, we have to introduce some other scalar field. I will not go more details, but later may mention the main results of that. Okay, with this kind of motivation, so let me just say the black hole. So how is a black hole formed? One way is actually if we have enough heavy mass of stars, eventually after they use up all the fuels, then it will end up to the black hole. Such things are about some tens of this mass of the sun. So that's what typical black hole mass is. Another thing is that there may be black holes with 1 million or 1 billion times heavier than the sun. So this one seems to be in galaxy, inside galaxy, including our own galaxy, there seems to be such supermassive black holes. So there are different types of black holes. And another thing is there is a primordial black hole. That means rather than due to the evolution of the stars, before everything is made, originally there was some fluctuations in the very, very universe. Any energy density fluctuation, if it is really highly fluctuating, then they can collapse into a black hole. That's the so-called primordial black holes. So, so if we have a primordial black holes, the evolution will be different with a primordial black hole and without primordial black holes. But I will not go any detail. So do we have actually observation? The reason I am saying is that until 80s, 70s, I do not know because I'm still too young to know all the development in 70s, but I'm old enough to know what happens in 80s, let's say. There was some division of the physicists. One group, okay, black hole should be somewhere. Another group, well, it's interesting theoretically, but no, black hole may not exist. So they just thought it's a mathematical artifact. What I'm emphasizing is that we are not talking about the mathematics, but real world. So actually, so the stellar mass one that has been observed through this black hole X-ray binaries. I will not go details. And also through the starting from the 2015, we actually saw the gravitational wave through the merging process of two black holes. That's the only way that we can explain that kind of gravitational waves. So, and also there are nowadays pulsar PTA observation. I guess Professor Qingguo Huang is an expert in this area. I just so here there is some also CPTA fast here also. And this one is somebody say that very super all the stochastic signals are from the supermassive black holes and pyramidal black holes. There are many explanations. And those are the observational things. And the supermassive black hole, like a million or a billion times bigger one, actually people follow the star motion inside the galaxy, very close to the center, and see. So if we observe the motion, then we can estimate the mass. So through that, they can estimate the mass. But getting mass does not guarantee that it's a black hole. So there are more things to do. But anyway, all through these kind of things, also finally, Event Horizon Telescope, they observed actually the shadow of the supermassive black holes, etc. So the result is that, have we observed the stellar size, stellar black holes? Yes. And have we seen some supermassive black holes? Yes. And usually the in-between is not easy. So here also, there may be some in-between the black holes or masses in between. That one, we don't know yet. This is the least known. So conclusion is that black hole does exist. It's not, we are not talking about some theoretical fancy fantasy. Okay, now a little bit more mathematical. We are given black holes. Then, in the simplest case, let me start from the Einstein gravity, even without the cosmological constant. Then we are given Einstein equation. Then the static solution is such that the metric factor here, F, is like given by this one. Problem is that we have in mind F should be positive. But actually, the solution here will be positive only R is.
你好，您是
They may say change sign.
哎呀，好，那个，现在就是我有一个学生，也是博士后，他现在跟我在算一个就是两次那个逆相变的一个工作，然后他说那个数据导不出来，他让我问你一点，我叫魏东东。
Here we can just write send the line.
啊，行，你帮他你看看是怎么回事？反正他说他数据导不出来，我们急着要看。
Usually can escape.
行，
However, if they are getting closer,
好，谢谢你啊，好嘞，拜拜。
What is happening is that so this is the such light cone. So outward, inward. So inward is always getting inside this R equal to 0. Passing R equal to 2GM, which we call as a horizon. However, if it's shooting closer and closer, and if it is very close to horizon at the 2GM, outward, inward is definitely inside, but even outside one, they are start staying at R equal to 2GM. So they are rotating there, and they cannot escape. Okay. So that's what horizon is. So nothing can escape if they are once at the horizon and the inside. So that was the condition, but I will not talk about anything. You may ask anything that I have not explained. Now, next thing is a little bit bothering thing. Black hole is thermodynamical system. What does it mean? So thermodynamical. Black hole is okay there. Thing is that it starts from the so-called Hawking temperature and Hawking radiation. So if you have a black hole, there can be some quantum phenomena. The virtual particle and the antiparticle will be created, and the one will be sucked into the black hole, and the other will be emitted outside. So by that process, if you just get the negative mass one, then you are reducing mass. So in other words, mass will be reduced while the some radiation will be going outside. That's what Hawking radiation is, which was calculated by Hawking in 1970 already. So according to that, if you have a radiation, then there must be some temperature, black body radiation. That temperature is here so-called surface gravity, and the F function dEGB. That's what it is. So in terms of dimension, so 1 over R, because F was dimensionless, and so taking a derivative with respect to R, that's 1 over length. So in other words, smaller and the smaller R means so 2gm and R and M is proportional. So R small means smaller mass, but smaller and smaller mass means higher and higher temperature. They are radiating faster and faster the energy. Okay, that's what is happening. And so this is the temperature graph, roughly speaking. Now, so this one is somewhat unstable. I'll just come to that later. So since we said that the black hole is a thermodynamic system, we have to say what is the first law, second law, and etc. First law here, the relation is that mass is essentially energy. So you can imagine some micro-canonical ensemble easily. And the bothering thing is entropy is area of the horizon. And temperature we showed before, just F prime, which is so-called surface gravity. So gravity is acceleration at the position of the horizon. Here, the main thing is the, let's say, entropy. So what I learned when I was undergrad student, that the entropy is counting the number of states, and the entropy is essentially logarithm of that. So in other words, e to the entropy is the number of states. So of course, if energy is increasing, we have more and more states. That's a typical system for any system. So actually, the increase is either power in terms of energy to become power. Then entropy is log E. But since we are talking about the area is R squared, and the R is proportional to mass, so mass squared or energy squared, because mass is energy. So usual the condensed matter system or any system we do know, if the number of states are increasing as a power, they are much carrying the entropy much smaller than black hole. If you think about some the exponential, even in that case, you get entropy is actually linear. It's much smaller than E squared. How about factorial? Factorial is the faster than exponential, faster than power. It's x to the x power. Even in this case, it's smaller than that. So as far as I know, I cannot find any system. I kept asking many of my colleagues, are there any system that entropy is given by energy squared, let's say? I didn't get any good answer. So in other words, black hole carries information much, much more than any physical system we do know. Entropy is really, really very good. Okay? And another thing is about the stability, heat capacity. And the heat capacity is, I wrote here details, so you can take a look. This is the heat capacity, and one more derivative that gives this stability. But if the temperature is dropping as R goes larger, then that means unstable. So conclusion is that black hole can be formed for any mass, and usually this heat capacity is negative, and that means instability of the thermodynamic system. Interpreting the black hole as a real system. It is clear because, I mean, they will dissipate away all the energy of the black hole. Black hole will be eventually gone by quantum process. However, if I am interested in the equilibrium physics, then I do need something, right? What can I do? Well, easy thing is what we typically do is put the black hole inside the box. Then the radiation will come out. But radiation, once they are arriving at the boundary of the box, they will be reflected and remain inside the box. So then there will maybe some equilibrium point, the Hawking radiation, and then the soaking into the surface. They will form equilibrium. In the case of the Einstein gravity, the short-circuit black hole so-called, since it is infinite volume, whatever radiation you emit, it will go away to the infinity and never come back. So mathematically, similar thing happens for the so-called anti-de Sitter space. In brief, it's the ADS. So if we put into ADS space, they are providing kind of wall so that the system will be stable. Okay, so let's go to some. Okay. Now, so then let's talk about rather than box, mathematically ADS black hole is better. So ADS black hole means we are introducing some this cosmological constant, but negative. That's it. This is somewhat familiar. Then conclusion is that we can have, in terms of the mass mu, before we wrote as a 2G n in 4 dimensions, but in general, that's why we wrote a mu. There is some term here, I swear. So, and calculate the temperatures, and eventually, if you plot temperature here as a function of the horizon size, you get this one is coming from the previous part. And this part is coming from this part. So roughly speaking, you may say that L is the size of the box. So in other words, if L goes to zero, infinity, so lambda, cosmological constant is 1 over L squared. So L goes to infinity, box going to infinity size means vanishing cosmological constant. So in that limit, so we'll be back to, so this, the minimum point will be shifted, and eventually this curve will be gone, and only this curve. That's what we have seen in short circuit. But there's actually usually two, this kind of things. Temperature is going up as R is smaller, or let's say the temperature is dropping, then increases again proportional to the size. So we call this is a small size. So for given temperature, this is a small r, so it's a small black hole. And this one is happens at a large r, so this is a large black hole. So in the ADS black hole, two things are happening. One is the so small black hole and also large black hole. This is due to such ABS effect. Okay, so as a result, if we just do the phase diagram, here at the above that minimum temperature, either small black hole or large black holes, and if you calculate the let's say thermodynamic potential, then you can see that small black holes are always higher thermodynamic potential than the large black hole. So it is a large black hole which is stable. However, there was some minimum energy, the temperature T0. What is happening below that? Then it is not black hole system, so we call it a thermal ABS system. So anyway, this way, what if here describing is that there is a phase tension between some thermal ABS to the black hole system. So the lesson is that we are converting, this is already a holography idea, we are converting usual phase transition in terms of geometric description, gravity description. Okay? So that gives us very, very powerful tool in understanding quantum system. Okay, so we can have some black hole with a charge, but here the one interesting thing is that the thermodynamics are ensemble dependent. I kept asking people, because this is in contradiction with what I learned in undergraduate. I was told that in the thermodynamic limit, whether you are relying on the microcanonical or canonical or grand canonical should give the same result. But here, somehow they do not give the same result. I do not fully understand. I just discussed with some of the physicists here, but at least I'm not, maybe, so you may know, but I do not, I was not really fully understanding. Yeah. Anyway, there is some dictionary between the bulk gravity and the boundary theory at the level of the generating functional. So it's there is some well-defined dictionary, Chinese to Korean, Latin. If you know one language, you can convert based on the dictionary. It's a really dictionary. Here, the thing is that if you have some charge, there's some the global charge, in the four dimension, there's some global symmetry, which means essentially number of particles or baryon number, so-called. So when we say the charged black hole, that means in terms of the boundary quantum theory, we are talking about some particle numbers existing, in other words, chemical potential. So in other words, rather than vacuum, we are talking about some dense media. Then to deal with the dense media, you have to study black hole, not only the mass, but also with some U1, the electromagnetic kind of U1 charge in general. Okay? That's the lesson. Now, so already, I guess it was too long. Let me be very sketchy. So if we think about some modified gravity with the Gauss-Bonnet, what will be the change of the black hole? Answer is that in the short-circuit case, any tiny mass can collapse to form black hole in the primordial black hole. However, here, there is some minimum mass, only some heavy enough object can collapse to black hole, and if they are light, they will not collapse. And so it's that's the most the bothering thing. So very different anyway. So you are introducing one parameter just like Gauss-Bonnet term, then you are given this kind of minimum mass. Okay? Now let's move on to the cosmology. So in the cosmology, for those who are not from the gravity, so here our universe seems to be homogeneous here, and there seems to be roughly speaking same. And the direction dependency is also negligible. In a large scale, of course, right? In the not small scale. Then that will give us that the metric we do need only single function, the so-called scale factor. In other words, size of our universe. And this scale A is really expanding. That's what Hubble found. So only one unknown function as a function. That is the so-called lambda CDM. So here, in the Einstein equation, how can we just factorize the right-hand side? Any single parameter is so-called equation of state parameter, which is defined as a pressure divided by energy density, which we call W. So if W is known here, then we do know we can solve this one. And here, if you see here, A double dot, this is acceleration, depends on rho plus 3p. So rho plus 3p means so 1 plus 3w. So 1 plus 3w sign is very important. In other words, w equal to minus 1/3 is very important. And if w is bigger than that, it's a deceleration with this minus sign. If it's smaller than that, like a w equal to minus 1, then it's acceleration. So if it is acceleration, that's generically we may call it as a dark energy. Okay, so here I don't have any time. I spent too much time here. So here typically radiation in the is characterized in terms of W. So radiation pressure is 1/3 of the energy density. As a result, they will be reducing by h minus 4. In other words, if universe is twice bigger, then it will be smaller than 2 to the 4. In other words, 1/16. That's the way they energy density is shrinking. So which I draw here as a green color. Mass is h2 because the energy is there, particle number is there, but only volume changes. So slowly dropping. And if in the case of W equal to minus 1, then actually they are not depending on this size constant. So here, if we go really high early time, then always the largest number, this one, so radiation will dominate. Then at some time later, matter will dominate. If we wait much longer, it will be dark energy, which will be dominating energy. So at this moment, we live in the time of dark energy dominating. In other words, our universe is expanding, but with acceleration. That has been measured in the end of the 20th century through the supernova observation. Okay. I will not go any detail of these things. Now, what is the major thing if we work with this extra term, Gauss-Bonnet term? Then the main message is that we have some new phase, actually. So here, I put red colored one is what is changing the Einstein equation. So Einstein equation is changed due to the Gauss-Bonnet term and the scalars that we introduced. So as a result, so that's a new kind of matter we may interpret. So there's some very early universe, some time that that new ingredient will be dominant. That's what we found. So so far, this is the same as a lambda CDM, but there's a new thing. Question is, what would be the implication of this new effect? Okay. Okay, that's all the solutions, but I don't think I can go any detail there. And let me just mention one thing that in the very early universe, according to the standard model of the elementary particle physics, we have some plasma soup. So there is a fluctuation, so energy density fluctuations, and eventually they will also generate electromagnetic, the gravitational wave, stochastically. And that will be very actually interesting. So according to the standard lambda CDM, if you follow the formula, the radiation dominant highest temperature will be determining the amount of the gravitational wave. If you introduce some new phase, radiation breaking into something radiation and all universe something else, usually since the temperature is lower than the almost emitting temperature, it will be producing less. So that means even in this lambda CDM, we have not seen any such stochastic one. By the way, the frequency we are talking about is about 100 gigahertz at the observation frequency, close to 100 gigahertz, very, very high energy. If you think about some order of hertz or sub-hertz, LIGO or LISA or TAIG, that's always a hertz or sub-hertz. But this is another extreme case. But anyway, so this one is very non-observable. But in our model, to say the conclusion is that typically this one is what is predicted in the lambda CDM. So this is the kind of bound. This red, the green line is the present detector's sensitivity. So they are way below. So it's hopeless to see. However, in our model, there is some enhancement that can happen. So it may just touch. If it is so higher, then there will be beyond some bound allowed by the BBN, Big Bang nucleosynthesis. So that way, actually, either we find or not find in the future, then that may say something about our universe, what is happening to the higher coordinate. Okay, those are the basic things that I wanted to say. So actually, in the gravitational wave concern, nowadays most emphasis is tend to be zeroth power and below. However, there is some worthwhile effort to push this one up because there are some sources and there are many models that may make those things be available and that may test our lambda CDM models. So to summarize, I just try to give you some the gravity theory beyond Einstein, whether it is needed. From the theoretical point of view, I emphasize that if we believe in the quantum field theory or effective field theory approach, there should be modification. The only thing is that there's a small and we have not seen them. But somewhere in the future, that may be observable. And that's the one thing. And as some simple model of the beyond Einstein gravity thing with some quadratic pieces, I just try to explain you what is the different property of the black hole. And that was so-called essentially the minimum mass exists. And if it's too small, black hole will never form in the primordial black hole state. And I didn't explain many things. And related to cosmology, actually one can play with some dark, what is the implication to the dark matter, which we have done, but I don't have any time to explain that. But one interesting thing is that since in China, gravitational wave is a really big topic. So here, another extreme high frequency of gravitational wave, according to our model, there's some possibility of watching some signal coming from very, very early. Okay? That's what all I'd like to say. Thank you very much.
Any comments, question?
Thank you for a very nice talk. It's very clear. So I got to be curious about the gigahertz gravitational wave you talk about, because as you said, there will be an enhancement between the lambda CDM and the dilaton-Einstein-Gauss-Bonnet gravity. So what's the I want to know the detailed mechanism. What causes that kind of enhancement?
Okay. Major thing is that in the all the energy stored in the gravitational wave, it's to me it's a very complicated one, but they are dependent on the evolution history of the universe. Here in the eta is a show viscosity, and there's some Hubble parameters coming in there. So the universe evolution history is important. But so all the known result that it is negligibly 10⁻⁵ or 10⁻⁷, smaller than what we can observe. Okay? That one is based on the lambda CDM model approach. However, if you have some different evolution, universe evolution is different. In other words, one example, rather than answering your gravitational wave, if we talk about the dark matter, let's say, like the WIMP particle, weakly interacting massive particle, thermal decoupling time occurs. There is some interaction rate, and the computing that with some expanding speed. If they are expanding too fast and too dilute, then there is less and less interaction, so that they will never be in thermal equilibrium anymore, right? So the evolution of the scale factor or Hubble parameter as a function of time is very important. In the new phase that we found, there's a very, very different evolution in terms of temperature, let's say. Usually, Hubble parameter is usually TT squared, but it's a different power in the temperature. So that's why we can get some extra enhancement here. Different evolution of the universe.
Yeah, so what's the equation say at that new phase?
Okay, very good question. I'm sorry that I skipped many details. So the thing is that we found if it is high enough, the solution flows into some fixed point. And the fixed point, these are the fixed point values. It may flow to the W equal to 1 or -1/3 or these kind of values, depending on the, this is alpha and the gamma, which is the alpha times e to the gamma phi in front of the Gauss-Bonnet term. So roughly speaking, as a function of Gauss-Bonnet term coupling, we can have some few options of the fixed point. Okay.
Oh, sorry. What is the source of the gravitational waves in this new phases?
Source is just the fluctuation. In this case, fluctuation of the plasma. So, if the question is about here, there is some natural fluctuation of the it's a standard model particles of plasma.
I see. Oh.
So that's it. So that will just induce us, give us some instantaneous quadratic moments, right?
So
So
they are
that's the-
similar. Are they similar to the scalar induced gravitational waves or something like that? Just in another kind of state.
I'm not an expert on that matter, but I think they should be essentially very similar.
Okay.
As long as you can have some source of the
Yeah.
such some quadratic moment, right? Here is due to the thermal fluctuation.
Any other question? How much?
I have a question related with the comments. This new phase in the early universe, I guess that it would affect the Hubble constant today, how we measure it. So, does this have any effect on the Hubble tension with new phase of the universe induced by this Gauss-Bonnet gravity?
Okay, so we thought about that, but I mean let's say whatever happens in the CMB, if it is before decoupling, like a redshift like 1,000, if it is a much larger redshift region, then they will be washed out. So I think unless we are talking about gravitational wave, which is decoupled from all the thermal system, but the photon is, unfortunately, I don't think it will carry any information.
Maybe I have a question. So what is modified gravity? So we know, so in modified gravity, typically they will introduce new polarization degree freedom for the gravitational waves. So what happened in this theory?
Polarizing.
Yeah, from plus mode and the cross mode. So do you have new modes in this modified gravity? And in this sense, how to define the gravitational waves in your talk?
Yeah, so if we are talking about the massive gravity, you are right. We are introducing some additional longitudinal degree freedom, which may be equivalent to some scalar. But here, it is Gauss-Bonnet, which is very special. Without coupling to scalars, they are not carrying any degree
Yeah,
freedom.
that's true. But you do have a scalar field.
That is right. So I think even that one should be very highly mixed up with that scalar field. So since we are already treating scalars and as well as the scale factors, I think in some extreme limit, we may say that no additional degree in the gravity part and additional degree from scalars. Another way is that let's say scalar may be kind of some longitudinal component of the gravity and like that. So in a sense, you are right, we are introducing extra degree freedom, but whether it is from some longitudinal mode of the graviton or scalars, that seems to be very hard to tell because they are highly mixed.
I see. Okay. So also a question, so you introduce a new phase beyond the radiation dominated area. So I'm curious, so when this new phase, begin? Because at the end, maybe you do the dilute of this energy. So then we have the traditional thermal history for the cosmology. But if we go back, so when this new area begin?
So that's what we have been working on nowadays.
I think.
But usually we do not want to be very drastic. So the standard picture is that if we just go backward then radiation dominant era will be going to just up to reheating.
Yes.
If we go further, then the inflation period.
Yes, indeed.
Inflation, then the reheating period, then the radiation dominating, right?
Yes, yes.
We'd like to sandwich in between. So, okay, inflation we do not touch. And after reheating, let's say, we have this new phase, and then this one.
I see.
So that's what we have in mind at this moment.
But in this sense, you should have a special mechanism to trigger this new phase, after reheating, right? Yeah, you believe it's the new theory, so we should find a new mechanism.
Right. Okay, so so in that sense, so at this level, such some tricky and very important thing we just deal with as some parameterization. Because if we want to really figure out the mechanisms and everything, we may be deviating too far away. That may be another research activities.
Yeah, my motivation is that. So because this is a new theory, this work for cosmology, maybe we can also test this theory from the black hole. Yeah, if we can know the mechanism to trigger this, this story. Yeah,
that's interesting.
Maybe if we believe some quantum mechanism near the black hole is also very high energy regime, maybe this theory can also work in that case. Then we can detect some signal, from the gravitational waves from the merging of the black hole or something else.
So at this moment, unfortunately, I do not have any very clear picture of how it is naturally evolving into the new phase.
I see. Okay, thank you.
But once it is in the new phase, all the remaining thing we do know because that's through the solution of the whole equation, modified Einstein equation, right?
Yes, I see. Yeah, because it's a high derivative. So typically it will be very important in high energy regime. That means
but even though it's a high derivative, every differential equations are second order.
Yes, that's true. That's true. Yeah. Okay, if we have no more questions or comments, let's thank our speaker. Okay, thanks very much. 大家可以门口签一下到，如果没签到的话，因为我不知道学生是不是没有考核，是不是？你们那个参加这个活动，行，我们可以结束了。如果大家交流没有的话，大家就Okay.
So this afternoon I'll be staying in the room 416, pistol room. So if you have any questions, I'll be happy to discuss with any of you. Okay.
4166 building.
Oh, this building, the fourth floor, one flight up. Yeah, 416. That's the pistol room.
416房间，如果你们想讨论的话
416
16
Yes, 416
Yes.
这里贴过啊。